Isaac Newton did some of his most influential work during his own pandemic, the plague of the 1600s. Staying away from school, while at home he developed calculus, developed his theory of optics, and also his law of universal gravitation. By the way, he was only 20 years old, so no pressure. Imagine Newton sitting under a tree and an apple falls. Does the apple accelerate? Yeah, it does. What force causes the apple to accelerate? I think we can all agree that it's gravity. Newton looks up in the sky and sees the moon. Is the moon accelerating? Well, it's moving in a circular path, so it must be undergoing a centripetal acceleration. What force causes the moon to accelerate? It was Newton's contention that both accelerations are caused by gravity. Newton didn't invent gravity. He proposed that it existed everywhere, that the gravitational force was universal. That all matter, which is anything with mass, exerts an attractive gravitational force on all other matter. Newton proposed two factors affected the gravitational force. First is mass, and Newton said gravitational force is directly proportional to mass. This is fairly intuitive. Something with twice the mass is twice as heavy. The second factor is distance. Newton determined that gravitational force is inversely proportional to the square of the distance between the center of mass of the objects. How can we verify this? It was known in Newton's day that the average Earth-Moon distance was 60 times the radius of the Earth. We can find the acceleration of the Moon to see if it fits this model. The period of the Moon's orbit is 28 days, or approximately 2.4 times 10 to the 6th seconds. The radius would be the average Earth-Moon distance, which is 384 times 10 to the 6th meters. So the tangential speed, which is circumference divided by period, is approximately 1,000 meters per second for the Moon. Centripetal acceleration is speed squared divided by the Earth-Moon distance. So the centripetal acceleration for the Moon is approximately 0.0026 meters per square second. Does this fit Newton's model? So the acceleration of gravity on Earth's surface is 9.8 meters per square second. The Moon is 60 times as far away, so 9.8 divided by 60 squared, or 3,600, gives us about 0.0027 meters per square second. So yes, gravity appears to follow what we call an inverse square law. Let's talk more about how an inverse square law works. Let's say we have an apple at distance r from the Moon, and it experiences a gravitational force of F. If the apples move twice as far away, how would this change the gravitational force? The square of 2 is 4, and the inverse of 4 is 1/4. So the new force is 1/4 the original. Now don't forget Newton's third law still applies. So that force is exerted on the apple is equal and opposite to the force exerted on the Moon. What if we triple the distance? Well, the square of 3 is 9, and the inverse of 9 is 1/9, so the new force is 1/9 of the original. What if we move the apple closer to the Moon, to say 1/4 its original distance? The square of 1/4 is 1/16, the inverse of 1/16 is 16, so the new force is 16 times the original. The law of universal gravitation allows us to find the actual gravitational force as well. The gravitational force between two objects equals a new constant, capital G, times the product of the masses divided by the distance between them squared. G is what we call the universal gravitational constant, and it equals 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Notice that this is a very small number. This really small constant reflects how weak gravity actually is compared to other fundamental forces. It requires enormous mass for it to be appreciable, like planetary sized. Let's take a look at a couple example problems. Two spherical objects have masses of 200 and 500 kilograms. Their centers are separated by a distance of 25 meters. Find the gravitational attraction between them. So we're going to apply Newton's law of universal gravitation. These problems are easy in that we don't have to do any changes with the or manipulate the formula at all. What makes them tricky is all the scientific notation. So we've got Fg is going to equal the gravitational constant 6.67 times 10 to the negative 11th times 200 times 500 kilograms all over 25 meters squared. I recommend multiplying the top of the fraction first, the 6.67 times 10 to the negative 11th times 200 times 500, before you do the bottom. If you're using your phone as a calculator, you probably have something that looks like this. You turn it horizontally and you get your scientific notation. So to do our scientific notation, I know sometimes you'll do times 10 to the caret, and that's going to mess you up. The best way to do it is to like this. So 6.67, and your calculator is going to have a button that looks like this, the capital E's, or it might say EXP, or it might say times 10 to the something. But you're going to hit that button, and that's going to take place of the times 10. And I go times 10 to the negative 11th. Now if I hit the equal sign, you can say I have 6.67 E, which represents times 10 to the negative 11th. Now I can multiply that by the 200, by the 500, and I get 0.0000667, or 6.67 times 10 to the negative 6th. So the top of my fraction is 6.67 times 10 to the negative 6th. Now I can square the 25, which gives me 625. So to get our final answer, we'll take our numerator, the 6.67 times 10 to the negative 6th, and we'll divide that by the denominator, the 625, which gives us 1.067 times 10 to the negative 8th. And we can round that to 1.1 times 10 to the negative 8th newtons. Notice that is a really small number. Again, like we said, in order to have an appreciable gravitational force, you need huge masses, and 200 and 500 kilograms just isn't going to cut it. So the second part of this, part B, how would this force change if the distance between the two masses was decreased by 1/2? So know that force and distance, gravitational force's distance, follows an inverse square law. And we're cutting the radius in half. We're doing half the radius. So if we square the half, we get 1/4. Take the inverse of 1/4, we get 4. So if the distance was decreased by 1/2, the force would be 4 times as great. Let's look at a second example. Two spherical objects have masses of 1.5 times 10 to the 5th kilograms and 8.5 times 10 to the 2nd. Their centers are separated by a distance of 2,500 meters. Find the gravitational attraction between them. So again, we're going to use Newton's law of universal gravitation, where our capital G, the gravitational constant, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Our two masses are 1.5 times 10 to the 5th and 8.5 times 10 to the 2nd kilograms. And our distance is 2,500 meters. All right. Again, you should multiply the top part of the fraction out first before you do the bottom. So we have 6.67 times 10 to the negative 11th. I'm going to multiply that by 1.5 times 10 to the 5th times 8.5 times 10 to the 2nd.
and that gives us 0.0085. So the top of our fraction is 8.5 times 10 to the negative third Newton meters squared. We square the 2500, and that gives us 6.25 times 10 to the sixth. So 8.5 times 10 to the negative 3 divided by 6.25 times 10 to the sixth gives us 1.4 times 10 to the negative ninth. Now, depending on your calculator, the answer you get may look a little bit different. What we just had showed 1.3 times 10 to the negative ninth. My regular calculator, handheld calculator, doesn't go out to that many digits, so it only gave me 1 times 10 to the negative ninth. All right, so either answer would be acceptable. How would this force change if the mass of one of the objects was triple? So before we looked at the change when the distance changed, now we're changing the mass. So gravitational force is directly proportional to mass. So we have 3 times the mass, which means we have 3 times the gravitational force.